Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So Christina Rotaro from Purdue University, and she's going to talk about building trustworthy wireless mesh networks.
Thank you very much, and thank you for the invitation. I'm very happy to be here. I have to mention that initially when Jitu asked me to give a talk, I was put in a very interesting position because I have many projects at very different stages. And actually the mesh one is the one that just started. So I wanted to bring, to give you a flavor of some of the things that my students and I are doing. So you'll see that there is a mix of several things. Just to motivate the work is that it's just I was extremely surprised to see the evolution of the wireless networks. I'm coming from a communist country, and several years ago, you could never see anybody with a cell phone. Now, what's going on there is, it looks like technologically many people are more eager to use things over there, one of the things that I listed here is just to show the mixture that we had in terms of the infrastructure versus lack of infrastructure, very ad hoc. We started, the cellular always had a very well-built structure. We had a wave of ad hoc networks, either Wi-Fi or sensor networks. And it looks like now we are going back to the structure. Both mesh networks and vehicular networks, they do have a particular structure that characterizes the network. And all of them bring different applications with either more military-oriented or more community and with more applications to everyday life. And one of the things that we like mesh networks is because they promise certain things, and one of them is that they provide increased coverage. Wireless has this problem that you're just limited in how much, to what distance you can talk with somebody. Hopefully, the inbuilt structure will allow us to have a more robust communication. So there are different type of services that you can start thinking about them once you have a more robust communication. And also the service is supposed to be better, at least in terms of bandwidth, by taking advantage of several things, including the multiple radios. And one of the things that I like to point out is that, and other people also notice, is that this makes this need for cooperation, just because you have all these participants that they're supposed to work together. And there are several things that they can collaborate in achieving the services. Now, cooperation brings many benefits, but cooperation also brings some pitfalls. And I'm interested in the problems that start appearing once you don't have only honest participants. And some of the behavior that we can see in cooperative networks are either selfish behavior or malicious. And this can affect both the structure of the network, but ultimately they can affect the availability of the system. And just to make a clarification between selfish and malicious, usually you have some chance of dealing with selfish because they still want to get something out of the system. So because they still want to get something of the system, hopefully there are some incentive mechanisms that you can offer them. It's much more difficult to deal with malicious participants because their goal in life is to make your life miserable. So it's very difficult to achieve anything in that direction. But we have some hope. Now, another thing that I would like to mention is that there is nothing new here in terms of the problem. The mesh networks are not the only networks that are cooperative. And there are at least two that I can think about. One are overlays, the other ones are ad hoc networks. And although the problems are similar, we have to deal with different challenges. And things that create a big difference are the mobility versus the fixed structure. And another thing is the communication medium. So, for example, just to look at the overlay, is that even if you will have the same type of fixed structure, you do have a different communication medium. And it is interesting because of that to look at what people already did in these areas. And actually, I will tell you some of the things that my students and I did in this area. keeping in mind that in spite of these similarities, whatever solutions you have to design, you have to keep in mind that ultimately your communication is still wireless, which means that you still have to deal with the fact that this is a communication that is just by nature less robust. You have higher error rates. You have to deal with the environment can affect your communication abilities. Also, where you're going to deploy your applications. Do you have many tall buildings around, and so on. Besides that, even if we are talking about mesh networks where you have you don't have energy constraints, the medium itself is a shared resource. And actually, when you're talking about an adversary, that can cause you lots of problems at much lower level. You know, even at the MAC layer, all you need is one malicious participant that actually can prevent the other people from even getting access to the channel. And last but definitely not least, again, the nature of the medium makes it more vulnerable, both to eavesdropping but also malicious attacks. And I like these pictures. I saw it several years ago. I think it's the picture that they used to attack AO211. And I recently saw it in a Law and Order episode. So it looks like it's still very popular. It's a popular antenna. So what I want to focus on today and to show you is some, I want to show two of the problems that we looked at. One, I looked at it in the context of a hybrid network that was using both cellular and Wi-Fi ad hoc networks. And the other one, I want to show a problem that, for me at least, it seems very interesting in the context of overlay. And it's an attack that is much more subtle, very difficult to detect, but it can go a long way. And I think that these things will show up in mesh networks too. And to put this in an even broader context, I want to show you some of the projects that we are doing in my lab. So I am interested in anything that is distributed and at the extreme Byzantine. We cannot always solve all the problems, but I first like to see what is the worst case that you will have to deal with. So the first project that actually just ended, and we went through a red team that was very successful, looks at how to build Byzantine resilient systems that scale to wide area networks. We were extremely happy because they told us that this is the first systems that they couldn't break. And one of the things that I think that made a big difference is the fact that the system itself accounts for insiders. So we didn't tell them, oh, just go ahead and find some buffer overflow. We told them, we can tolerate X number of malicious insiders. These are the servers. This is the code. Do whatever you want. And so it's the nature of the approach that actually I think made a big difference. Now the other three projects, two of them focus on wireless, one of them focus on overlays. And the one that I'm definitely most excited about is the last one, which just started, and what hopefully will put together some of my previous work in collaborative applications with this environment of mesh networks. So let's get started with the first thing that I want to talk about, which is this multi-hop nature and the problems that can cause in terms of security. And because of the fact that in wireless communication, really there is no other way to reach other participants, this creates a big difference in terms of how do you design protocols, including starting with simple things like routing. And such a malicious or selfish attack or selfish behavior can have an effect both on allowing other people maybe to obtain free service or ultimately to affect the availability of the system. Now, one of the problems that my students and I look at started with looking at cellular networks. So they were very excited about 3G services, and people like everything that it has some type of graphic and video. Somehow they can relate better with. I always had a hard problem also as a student to sell networking because you couldn't have cool demos. So you cannot show, oh, but see, this graph is so much better. And somehow people from graphics, they show a cool picture, and that did it. So what we actually looked at is how can we actually improve the quality of the service as the client goes further from the base station by using ad hoc nodes, having AO211 cards. So the idea is that you can get these type of things by building some type of routing structure that allows nodes to adapt based on the bandwidth that they're perceiving, that they have. And things that we dealt with, we wanted a better throughput. We looked at how to use multiple channels, or if we'll have them, how that will improve. We looked at interference and how that will affect when we make our decision of how to select the parent in the tree structure. And we also look at what will be the overhead of maintaining such a tree, just because, again, these are control messages, so the less you send of them, the better. And well, one of the things that we came up with, we showed that previous approaches that were just have a very greedy and aggressive nature actually were not performing as well as expected. So we came up with the idea of maintaining and building this spanning tree. And one of the big issues here were how can you build such a tree such that you do not pay a lot of cost in terms of overhead messages. And also, because, for example, one very trivial way you can do it when you want to add one more flow and download from the base station, one thing you can do is you say, okay, every time I'm adding a flow, I'm going to contact the base station, and everybody's going to adjust and rebuild the tree. But that means lots of messages, which if it puts it close to flooding, then why would you not just do flooding? So we wanted to do better than that. And one of the things that we came up with, actually this is what my students came up with, one of them really likes trees and really likes all kinds of trees. So he thought that topology trees will be a very good match for this particular problem, because what topology trees allowed us is actually to map this routing tree into operations on a topology tree that put us in terms of messages going from linear to logarithmic bound. So we spent a lot of time getting this working and designing how these operations will be performed and proving that we can get this log n, and have also examples of how would you even, for example, add or delay or decouple somebody from the network, how the translation will be in these operations. And when we got all this and we were very happy, we had one more thing that we thought that we had to deal with, which was how accurate the tree is. Because the moment, again, this is based on probing, so the more more frequent you do the sampling, and this refresh rate defines the sampling, the more often you do it, the more accurate the tree is. But at the same time, you have a higher cost going on in the network. So we also looked at what will be in this context, what will be a refresh rate that will behave relatively well. Did some simulations. Also look at the as I said, the throughput. We did some simulations. So I'm just showing this to motivate how in the end we come out to the security. But at least we could show that we are doing much better than if you have only base station. And with the green, for example, it's the optimum. So we were relatively happy about the results. We looked also at multiple flows and how we have multiple flows, how many of them we can sustain, how the multiple channels will help with that. And once we did all this work, we said, oh, and now let's think about security. And that's not the right way to do it, because you actually have to go back and look at other things to change many of the things that you already did. So there are things about this particular application that actually help us in dealing with security. And what I want to point out is that on one side, if you look at the regular cellular model, you start with the model in which the base station is not only the one that provides the service, but it's a central point of trust. And it allows you to build other services, even something simple like authentication and secure communication. The moment you throw in all these participants, all these ad hoc nodes, you completely change the trust model. And that's what creates the big difference on how would you accommodate or to what degree you can prevent against such nodes, assuming that they have either malicious or selfish behavior. And things that, for example, are negative is, relying on honesty, it's not always going to work. I have a professor when I was a student at Hopkins that he had the same theory about internet. Internet is like communism. It's supposed to, it's going to be free and fair for everybody, but somebody's going to do the work. So in the end, it's not going to work. You cannot have this working without some economic model. And the same thing here. You cannot assume that everybody always going to be correct and they're not going to take advantage of the system. So looking at the honesty, if you really rely that nodes are always going to report correct performance to their base stations, and they're not going to try to abuse the system, I think that you have a very optimistic view of the world. So things that can go wrong, it's either freeloading, which this is the best case actually, or you can also have people abusing the system in the sense that just creating denial of service by issuing many requests, and this is always an issue with distributed systems. Now another thing that, as I said, can affect is the way nodes will report, how accurate they will report their performance. And they can do this either because they're just curious and they just want, for example, to obtain some privileged positions in the routing structures, allowing them just to see more of the data that people are sending around, and maybe using later on for other things. Traffic analysis is one thing that people don't talk very much about, but actually it's done and it's an issue. Or they have other intentions. Now, one thing that I want to point out about this particular system is that you will always have a service, because all this, we started with the cellular. So which means that clients will always have at least the cellular service, because the base station, it's there for them, so they can get their service on the cellular channel. At the same time, so the malicious ad hoc may not necessarily be able to prevent the service completely. However, it's all a matter of perception. So if you manage to create the perception that the system is really not behaving correctly, and you manage to really reduce the trust that people have in the end, you actually achieved your goal. So even if ultimately they can always get the service via the cellular link, if you manage to convince them that things are not working and the purpose of having the ad hoc there, they're not reliable, you manage to create enough damage in terms of the reputation of the system. So, and of course, I didn't mention authentication, but most of the problems in network protocols, that's where they start. So people talk about complicated attacks, but there is nothing you can build in terms of security services before looking at authentication. Without having authentication mechanisms in place, there is not much you can do about it. So there are several things that we looked at. As I said, authentication is a big deal, and in this case, is not only authenticating participants that are part of the network, but in multi-hop network, in multi-hop routing. Energy constraints. So the batteries are. Thank you very much. So one of the interesting things with the multi-hop routing is that it's not enough to have authentication of the people in the network. Actually, many times you need to have authentication of the path, hop by hop. So we look at things like that, and again, we build on the fact that this particular application has a central point of trust, which was the base station. Also, we look at how to design payment rewarding mechanisms that can prevent freeloading and also can deal with some type of selfish behavior where they want, for example, if some selfish nodes, they would actually collude and they would like to add other nodes in the network just to be part and get the service. We also look at much stronger things like how would you detect malicious behavior in this particular context, where malicious behavior will be, for example, selective dropping of packets. And as I said, this problem is actually it's less difficult than when you have a completely ad hoc network, just because you have this natural point of trust, which is the base station, and because you do have point-to-point communication. So multi-hop communications, one of the reasons that it makes things very difficult when you look at insiders is because you do not trust that the data really will make it, just because you have intermediate nodes. So we take advantage of the fact that we do have a point-to-point communication, physical communication, which is the cellular, just to see to what degree, how far can we push this. So things that we did, we modify, for example, in the previous protocol, we had this path reservation, which means adding and adding flows when a node wants to obtain traffic. So we modify that to have it a secure path reservation. Not only, as I said, authentication is a math, but that's not the difficult problem. But there were things that we build on here because the base station is really the one that can see that the traffic indeed was, or because the base station is the point of trust, nodes can report to it, and the base station is the one that can actually make decisions with respect to giving credit. There are other things that you have to deal with because on one side, for example, we said, oh, it's very good to have this point-to-point channel, but you cannot send so much on it. So if you, every time you have some control information, you say, I'm going to send it through the cellular link, you actually get into other problems because you're going to have that becoming a bottleneck in your system. So one of the things that we looked at, for example, in terms of the payment, we wanted to capture this, on one side, just the charge because you're using the system. We also wanted to capture, have some cost just because people are initiating this protocol to try to prevent some type of denial of service. And also, we wanted to capture this notion of crediting intermediate nodes that actually do behave correctly in the system. And these three particular things covered it, and we also had some mechanism that actually we could show exactly on how much of the malicious or selfish that want to add extra nodes we could tolerate based on some parameters that we adjust in the last component. Now, besides that, one of the problems, it depends, of course, of your application. Some people think that if you lose packets, it's not a big deal. But if you would really like to look in an extreme adversary environment where you have nodes that maliciously will drop data, the question is how can you route around them? And should you take them out of the network or not? For example, here my approach is that in a network like the cellular and the ad hoc, taking them completely down can actually hurt you because you can partition your network, and as long as you can get them to transfer some, assuming that it's not completely that they will drop all the packets, but selectively they will send something, you may want to keep them in the network, but just decrease the likelihood that you're going to use them. Now, another big issue here is, for example, assuming that you do not trust, you trust only your source and the destination, how do you know who's the bad guy? Well, Alice says that Bob is the one that is causing the problem, and Bob says that Alice is the one causing the problem. And actually, we know this from fundamental distributed systems results that you cannot have agreement in this context. So it turned out that actually in the case of this application, we care much less about who was the malicious. We cared about the fact that the link was bad. So we actually penalized both of them. That was our approach in this context to deal with this difficult problem. To say, fine, all I care in the end is if the data makes it or not. Now, another thing that we also did in the context of this problem, because I said we didn't want to take the nodes completely out of the network, what we did in this context, we actually tried to bound the amount of data that we could lose on a particular link. And we had our mechanisms that assigned costs with each particular link took into account exactly this. How do we reward them and how do we penalize them such that over time, if over time they do send a particular or they relay on a certain amount of traffic, we consider them that that's good enough to keep them in the network, as opposed to taking them completely out. Because taking them completely out also what brings into place is that when people start blaming each other. So that's one of the problems always with the blacklist. They start blaming each other. There are other issues that come into place in this case because what we were doing basically, we were looking at just having feedback back from the client that indeed data make it. So in a previous work where, for example, we look at just pure ad hoc, we had a huge problem just because the messages, the probes and the acknowledgements themselves always went through the same path as the regular data, which means that if you do not make them looking like regular traffic and you can allow the adversary to actually be able to distinguish between the real, between the control, which is the probing and the acknowledges, and the data, they can trick you very easily. And we had ways to deal with that in that context. Of course, cost is not, I will not hide it. It's extremely expensive. Cryptography protocols usually, they come with a certain cost, and communication, it's even more. But again, here what we could do, we actually had some heuristics. On one side, we could use the point-to-point channels, and then we used some heuristics such that we could decrease the cost of sending this feedback back to the base station. And these are some of the issues that we looked that in this context. Now, switching gears a little bit, what I wanted to talk about is another problem that I found very interesting. And this relates with the fact that today many networks, self-organizing networks, they rely on some type of adaptivity mechanism just to optimize whatever the goal of that network is. So in the case of overlays, for example, many of them are built to optimize bandwidth primarily and latency secondary. And the way this usually, at least so far, people look at it at the positive aspects, which is nice. You do, there are systems out there that can really show you that you get very good benefits by performing this type of adaptivity. At the same time, once I'm looking at that these systems are actually end systems, if I take into account that maybe one of them maybe will not behave correctly, and once I say one will not behave, the question will be, why just one? Because whatever the reason may make one machine to compromise, you cannot assume that you're going to have in all your network only one malicious participant that will not behave necessarily according to the protocol. So there are several attacks that can happen, and to analyze this problem, actually, what my student and I look at, we picked on ESM. Well, why ESM? Just because we had the code available, and we were knowledgeable in how the system works, so we could actually go through the whole deal and actually running experiments and getting the real graphs that show us that attackers can cause problems by exploiting adaptivity. So in the context of multicast overlay, the main feature that we looked at is this fact that the tree dynamically adapts to maintain certain application-centric metrics. Bandwidth primarily, latency, round trip also, it's another one that, for example, ESM looks at. And you have, the logical, in the case of ESM, for example, there are two logical networks and one physical. Two logical because besides the multicast tree, you actually have another network that is doing the control messages with respect to maintaining the membership of the nodes that are part of the overlay. Now, the way this adaptivity works is based on two primarily sources of information. One of them is a passive observation of what the node perceives to have from the source. Another one is actually obtained from neighbors through periodic probing. So we call one primarily, the other one secondary. And based on these metrics that every node, as I said, one is from the source, the other one is periodic probing, they actually build, every sampling period, they will build utility functions, or there's three supported, but there will be some utility function. And based on that utility function, we'll make a decision if the performance that is getting at that point is good enough. And if it's good enough, nothing happens. If it's not good enough, then we'll make the decision to change. So the observation is that actually it is very important to have either an accurate reflection of the network conditions in the way it is reported by the probing nodes, or that the information itself is correct. Because if that is not the case, then you may end up making decisions that you don't want to. So to give even more details, actually the way it works in the case of ESM, it's a more complex, that's another thing that we like it, is because it uses many techniques to deal with several problems that appear in the context of adaptivity. And in this case, like damping and flash crowds and all that. So they have some inbuilt techniques that can look at it. So in this case, basically what actually happens in the end is that you have a short list that it's prepared. And the utility function is not the only one that is taken into account, but you have also some randomization factor that decides if you're doing the switch or not. And basically when we looked at it and all the design, we said, this is not built to withstand malicious, but it looks like actually has very nice mechanism. Actually, it may work. It may be possible that our attack will not be successful. Just because, as I said, there are these small engineering things that actually can allow him to detect, at least that's what we thought, some of this malicious behavior. So before going to the attack, we look at what will be things that can go wrong, assuming that I can make the network to adapt in a way that the adversary controls that particular adaptation. So one of the things with the trees is that trees are on one side, they're very good in terms of performance, but when you look at malicious environments, they're actually pretty bad. And the reason is because, once you get one of those adversaries to control a particular node in the tree, the higher in the tree, the more power he has. And unfortunately, one of the things that, for example, the attacker can do, and we were managed to create this behavior, is by consistently lying about the metrics that he perceives, he went higher in the tree. So he went higher and higher and higher. Of course, he cannot say that he's getting better than the source. So we checked that, and that worked. Usually, simple cases of no. Definitely, that was detected. He couldn't say that he gets more than the source, but still could get higher in the tree. And what that allows it is to actually control, as I said, significant traffic. What he decides to do afterwards, it's really his decision. Now, another thing that can go wrong, and this is also a very interesting attack. This relates more with freeloading, but also with displacement of nodes, is because the node is inside. One thing that he can do, he can actually make nodes to detach from a particular node, either by lying or by filling up. It's very easy to fill up the pipe, just that particular link. And because the attack, the amount of traffic, actually what we showed is that you have to send very little traffic just to fill up that particular. Oh, God. So because the amount of traffic that he needs to send to do that is very small, that's one of the problems with detection. So attacks that actually send lots of traffic, they're easy to detect. If you send very little, it's much more difficult. And the attack with the TCP is one of the first that actually showed that once you can create small bursts for very short time, exactly when the system is supposed to adapt, then it's much more difficult to detect. So this was another thing that we looked at. Now, finally, it may look that this is not a big deal, but the adaptation itself can create instability. Maybe now is the time to put to work. I took lots of control theory. My undergraduate degree was in engineering, so all those control theory classes, I think that now I can make good use of them. So instability, it's a big issue. That happens, also can come up in many distributed systems where you want to maintain some type of, for example, membership, and people just kept, coming and leaving, coming and leaving, coming and leaving. They can create lots of instability. So this was the third thing that we identified that can be a big issue. So what we did in the beginning, we just looked at the system, in its deployment. We took ESM, we got a bunch of nodes on PlanetLab, and we said, let's take only one attacker. But what we want first, show that we can move it up in the tree. And once I move it in the tree, just to show how much control he will have over the network, just do dropping on that. Just let's drop data on that particular node and see what happens if the system reacts. And to our biggest surprise, the system actually did not react. And for 20 minutes, we measured it. So we ran it for 90 minutes. For 20 minutes, nothing happened. Which, if you think about the way, for example, the system was deployed primarily in conferences, a talk is 25 minutes. So if out of the 25, you don't get 20, probably it wasn't a good use of your time. Another thing that we also looked at, we looked at what type of instability is caused in the tree. How many changes do actually you start seeing? And we were also very surprised to see how many changes in the tree we see just because you have one malicious node that consistently keeps telling that I have this high bandwidth, I have this small latency, I have. They cannot affect the RTT in both directions, right? Because the RTT, they can never make it better. They can always make it worse, as opposed to the others where they are the ones issuing the information. Anyway, so then we said, okay, let's get more of them and see what can go wrong. And of course, this proved what is something that, as I said, it's very intuitive that the tree is not the right structure to do this. But see, the problem is that if you want performance, usually people go with the tree and they think about the security afterwards. And it turns out that the tree is not the right structure for this. Now, this is another attack that when I was mentioning before about detaching the nodes, this is actually where the fact that the way the physical connectivity maps to the logical one was exploited by the node actually by the malicious node to make a node detach. So this is very detached from the source. So this is actually very bad because the node C was connected to the source. And how better than that do you think you're going to do than being connected to the source? And we actually make it connect 3 hops later, and we didn't have to send lots of traffic. Now, looking at the big problem, as I said, there are 2 primary sources of information. And if you really want to see what are the things that you can deal with, what you can do, you have the adaptation process, which is just information that comes into the node that makes the decision. Maybe some of the bad decisions you can detect them. Like, for example, dropping of data. If indeed it's something that it's observable, you may detect. But if the goal of this particular attack is, for example, ultimately traffic analysis, you have some colluding adversaries, how do you know? You're never going to know what happened. If you do not know that these particular nodes really do, playing an unfair game, actually see lots of the traffic in the network. So we have the detection that sometimes it may work for some attacks, but not for all of them. Of course, you have to have some type of response. What do you do, assuming that you do detect what the malicious? What would you do with them? And overall, I think it's always good to look at how do you improve stability. So these are all big issues, and we look at all of them. But what I wanted to show is some things that you can do to prevent bad adaptations. In the sense that have some smarter choices. Give the node that makes the adaptation some smarter choices in terms of the data that you make available for them. So the first thing that I want to mention is that when you are dealing with malicious adversaries, you cannot always solve the problem. So there are cases in which there is no way you're going to solve the problem. Simple case, well, if your malicious are majority, what do you think you're going to? There is nothing that you can achieve, right? So there are some assumptions, or there are conditions under which you can get some type of solutions. But even there, even there, if you can get some solution in general, most of them are extremely expensive. So the only way you can cut some of the cost is really by tailoring your particular. We know that we like everything to be very general, but because of the cost, the only way you can get this to be less prohibitive is by really tailoring on looking at the nature of the application and the problem that you are solving. So when you cannot do, yeah, go ahead. Sorry.
Do you consider it a bad adaptation if it actually improves your performance?
No. Because let's say
the attacker screws up your performance because he wants you to adapt in some other way. So you are technically doing better because you're avoiding the adversary's vileness by adapting. That's not a bad adaptation, even though it was. It's still not. It's not a bad adaptation if it improves your loss by preventing the attacker from making things worse.
No, I think that what you're saying is maybe that by adapting you actually get less performance, and you think that I'm considering that good. Is that what you're saying?
Let's say my goal is to get you to come off the parent. I'm a malicious attacker, and I want you to catch the parent and go lower down.
That's one.
So the way I do that is by giving you terrible performance when you're attached to group, and giving you and stopping my attack when you're not.
Actually, it's not giving; it's lying. Yeah.
So suppose I do that not with lying, but with a denial of service or something. Suppose I actually make it worse when you're attached to the parent than when you're not.
Mm-hmm.
Is it considered a bad adaptation for you to detach from the parent?
So first of all, that's a different type of attack, because it's denial of service. The reason that I do not consider or I don't look at denial of service is because I think that you can detect it with other mechanisms. What I look is that things that it's the nature of the information is not the quantity of it. But that can be an example. But denial of service, I think you have different methods to deal with it, and almost any system that I look at, they are susceptible to that. You know, if I go back to the wireless thing, I can tell you, that we have the best protocols in the world, and you can just come up and you just jam the channel. I know a Panasonic phone that when we had that in the lab, nothing worked. Whatever best routing we had there. So I think the denial of service, it's a different. But you're right, that can cause problems. Now, to go back to this, one thing that I want to mention is that I was talking about the nature of the information and exploiting application-specific semantics, because otherwise you cannot know if that is good or bad. There are cases in which you can never know if the information is correct. Is, for example, if you always have one source of information and there is no way you can corroborate that, then you're in big trouble. In fact, most of the distributed system protocol, the way that they deal with this, they say, well, we assume you have somebody that is correct. We keep sending to everybody. We learn what everybody knows, and we do some voting on it. But the assumption is that everybody has the information. If you have one person generating that, there is not much you can do. However, one of the things that we could exploit in this context, which I found interesting, is the fact that what you can look at the attacker is that consistency, right? So if he's not consistent in terms of the nature of the information, maybe you can make his life difficult, in the sense that you have to make him to do a better job at lying when he's building the information that he's disseminating. So what are things that consistency that we looked at? One of them is, remember, if I have appearance around me, right, and I do have a mapping of the physical and the logical network. If I know this type of mapping, and you're here and you're telling me that you get this great performance, and all these other nodes around, they are telling me that this is not the case, maybe I can infer something that shows me there is some inconsistency going on. Another thing that also was interesting in this case is the fact that there are several metrics that are taken into consideration, and actually they are not independent. There is some relation between them. So you cannot tell me, that you have a great bandwidth and the latency is not somehow related with that, or the RTT with the latency. So this is another thing that we thought about exploiting, the fact that the metrics that are reported, you have to present them to me in a consistent manner because they're not independent. And the last one, which is the most natural and most of the systems do, is looking at behavior over time. And that's the most easiest to look at. So what we actually wanted to have was some method that will not require any additional communication overhead. And what we look at, how can we do outlier detection on this data that it's reported, exactly exploiting these consistency issues that I talked about, primarily the one with relation to the space, to the time, and the other one related with the space. And in the context of the space, exploiting the fact that there is dependency between the variables reported. And Aaron had a lot of experience in intrusion detections, and he thought that this particular distance it's a very good match for our problem that we were trying to solve, exactly because of the fact, Mahalanobis Distance, exactly because of the fact that it captures this dependency that exists between the features that we are examining and we are making the adaptation based on. So what we did, we basically build two methods. One that I said look at the spatial. So by spatial, what I mean, how other peers are reporting what's going on in around, and also what is the relation between the variables reported by each particular node. So we call this spatial. The other one that we looked at was the other one that we look at is the temporal, which was how it behaves over past. And of course, we had some problems. Just to give you one quick thing, the difference between what you put on the paper and when you run it in the lab. So one of the things that, for instance, we run into, which are things that are specific to this type of systems, is what happens if there is no variance. So, well, this is one particular case in which you have to decide what you do. We run it on PlanetLab, lots of variance. Everything works fine. We have some other problem. We move it in a cluster, no variance. So these are all type of things that showed up, in real deployments, and we had to come up with some heuristics with respect to how to address and how to bootstrap the system in the first place, and in the second one, what will we do in that particular case. Now, another thing that, and we had a way of combining this together just to have a method in which this will be integrated in the utility function. What we did, we start writing a bunch of experiments with the new methods, looking both at the temporal and the spatial, and they definitely show that they can address the big outliers. Now, one thing that we didn't do here, again, we didn't look at what will have colluding. So this is just the first step of how would I deal even with the simplest problem just to take out these big outliers. So in this case, we didn't look at colluding. But another thing that was surprising for us is by just integrating, just by making this data to reflect or to avoid these very big changes, we actually improved the stability overall of the system. And we always plot bandwidth. So actually what happened is, although we did less changes, the bandwidth never went, each node never reported the bandwidth going down, which means that there were unnecessary changes that the system was doing. And this is something that as I said, we continue working on, and we'd like to take this to looking at also at colluding nodes. Yes?
But doesn't outlier detection allow malicious participants another lever with which they can affect the system? They could, I can make...
Yeah. So I know what you mean. That's why you have to combine this with some response mechanism. Over time, you can make this, the outlier mechanism itself, particularly the temporal one, which is something that we run into. This is a problem with all these type of systems. Yes, you're right. That's why one of the things that is very important is how would you react. And another thing that we actually do in combination with this, we actually look also at global context, because we do have the source, and we also look at the mapping. So for example, what global context can allow us is to combine this with information between the node and looking at the whole path. So we can build in terms of the reputation of the nodes, also of looking at what's going on over the path and what everybody's saying, just to have more, how can I put it, basically increase or decrease the reputation of nodes by using several sources of information. But one thing about this, what I want to point out, is that basically we did not add any communication overhead in the system. All we did is just improving this, the taking out at least the big outliers. Okay? And I want to be on time, so just to summarize, it's not enough to look only at the fault tolerance aspects of the protocols without putting security, because actually I have even more examples of how the moment you put security into the system, it may change completely your design. Some people will just go and say, well, you want to do this resilient, maybe the tree is not good, just give up the tree. Why not send 5 copies? That's what some people propose, right? You go and do multipass, but that changes really the initial design and goal of the system. Now, in terms of the security, I think that although it's very important, you should never add security such that you make this unattractive for the clients, because they're not going to use it. There's many examples in that aspect. So one way I can see always that how can you go about it, in terms of research, we are always trying to look at the stronger things, which usually come with some cost. But when you are looking at practical applications, the critical aspects are the nature of the application and the environment. Actually, the environment is the one that triggers most of the security concerns that you have. With the same application, you develop into different environments, and you may have different security requirements. And there's some techniques that I think that they can be incorporated in the meshes, because you're going to have similar problems that the ones that I described. And just to finish, things that we are working on right now. So, for example, we are looking at what are security problems in geographical routing. On the overlays, I look also at very basic security services. If you want to integrate very simple things like queue management, how does that actually affect the performance of your system in terms of burst traffic, in terms of even how would you do the reliable dissemination? Because these are very particular control messages. All you need is to lose some key in the beginning, and you actually are not going to be able to decrypt the information afterwards. I was mentioning the global information in the mapping between the physical topology and the logical network. Finally, we are also, as I said, I'm looking at collaborative applications in the context of mesh. And there's three things that they're now on the table. One is distributed infrastructure access. The other one is how to do secure multicast in a many-to-many environment, because that's what people want to do. They want to do chat. And the last one is how would you do available information access, because the robustness or the increased robustness at least allows you to think about it in the context of ad hoc. Or if you could talk, it was, or if you could rely on information, that was good enough. But having really a high available system, I think, would have been more difficult. And that's it. And I'd be happy to take any questions. Thank you very much. Thank you very much.